Welcome to CS3510. This is L07, right? 7A. Topic of today is Bellman-Ford. Rather, it's a bit expository on like Dijkstra's and when does Dijkstra's fail. So first off, let's talk about what a greedy algorithm is, and then we'll try to phrase this back into the problem that we're trying to solve. What is a greedy algorithm? We can consider Dijkstra's to be a greedy algorithm. We can consider the MST algorithm to be a greedy algorithm. There are many other greedy algorithms. But a greedy algorithm in some sense is one that makes very small, local, naive decisions, and somehow a sequence of tiny decisions that solve tiny problems snowballs into an answer that solves the entire problem. Now, if you're an introductory programmer and you have programming skill but not computer science skill, which everyone starts out that way, every algorithm that you ever implement is a greedy algorithm to first start. But know that a greedy algorithm does not solve everything. Suppose you have a literal knapsack here, and it's got capacity of, let's say, 90. And you want to fill as many things as you can into this backpack. And there's only a few boxes. There's a box of size 40. There's two boxes of size 40. There's a box of size 61. And let's say there's a box of size 30. Okay? So there's 4 packages. Each one has a weight and let's say even a value of these numbers, and that you can only carry 90 things, 90 units of weight, whatever they are, gold bars or whatever. A greedy strategy would perhaps pick the most first. You want to maximize the amount that you can take. So like just pick the biggest one, and then you put that in the car. But if you pick the biggest one, well, hold on. Did I do this right? Yeah, if you pick the biggest one, you can walk out of there with $61 or whatever, units of something, but you can't really pick anything else, right? If you try again, let's say you try the smallest one first, you're also not going to get the optimal. If you pick the smallest one first, you then have 60 units remaining. You can't pick that one, but you can pick one of these, but not both, so you pick that one. So you could walk out of there with 70 units of something, but what's the optimal here? Yeah, you can pick these two, and that'll get you 80. Right? So for all possible combinations of objects you could walk out of here with, and this is called the knapsack problem, we'll talk about this more extensively, it cannot be solved in a greedy way. And the reason it can't be solved in a greedy way is certain decisions you make locally prevent other decisions you can make in the future. If you choose the 61, you're eliminated all the other options. If you choose the 30, you've eliminated the 61, and so on. Right? So knapsack is known to not have a greedy solution because decisions eliminate other solutions. And this is like very high level, vague hand waving. But recall the reason that Kruskal's was a greedy algorithm was able to succeed. We were able to assume inductively that X was in progress towards some MST, and that if E is chosen through a very local, minimal decision-making way, it's the least edge that doesn't form a cycle, X plus E was in progress towards an MST, maybe a different one, but some MST, right? Kruskal's is a greedy algorithm because at each point it chooses the smallest edge with a certain property that it wants. And then it just adds that to its solution, and it's in progress towards a solution. So, and it was very surprising to us that such a local, small procedural thing works. But it doesn't always work. And in fact, in general, we have a good understanding of when do greedy algorithms work and when do they don't. Without getting too formal into mathematics, you can talk about, I don't know, matroids, whatever you want. When exactly does this work? When exactly does it doesn't? Is intuitively, if you think, is my local decision in progress towards a global decision, like a global optimum, right? Every problem can be approximated, perhaps poorly, but close in practice with a greedy solution. But we're concerned when you get the optimal. And for example, let's suppose you're minimizing a function. A function like this can be minimized quite easily by a greedy method. If you're at some point, you guys may know what this is called, you go down until you can't. That's greedy. You're like, I'm going to take a step downhill. Sequence of such steps will get you to the bottom. Did anyone know the name of this? It's got actually different people call it different things. That's not totally incorrect, actually. Okay, you start somewhere, you go downhill. I'm being vague on what that is because it's not. That's a different class. But what if you have a function that does not have what does anyone know what this function is called? Like functions with this property. convex. Or concave, I guess. I don't remember which one's which. Anyway, suppose you have a function without such a property, okay, which many such problems have. Let's say this was the actual minimum you were looking for, but you had something that looks like this, right? If you're here and you try to go downhill, you'll go downhill until you can't. You'll be stuck here. Because if you try to go uphill either way, you're going to get, things have to get worse before they can get better. So you won't ever find the actual minimum because you're going to be stuck at some local minimum, something like this. So in such situations where the problem can be, subproblems can be visualized in such a way, a greedy algorithm will not work. Greedy algorithms work in this, they don't work in this. That's kind of the intuition. And you could build, it's important to build good intuition when greedy algorithms work. Because greedy algorithms are fast, usually. They're really nice. I mean, this was simple. Kruskal's was simple. Dijkstra's, in some sense, is a greedy algorithm because things get to exit the queue when we confirm that there's a shortest path. We already get to know that there's no longer path without having to check everything. We just update a few edges, give us a few more pieces of information. We make some small updates, and we can say, oh, this one's done. We don't have to. We know it's found its shortest path. The motivation, what I'm saying here, is that we are going to concern ourselves with the case of computing shortest paths in graphs. So we're still in the context of single source, shortest paths. So the sum start, single source, and we're looking for the shortest path, where the shortest path is the sum of edges. But now we're concerning ourselves where the weights of certain edges is allowed to be negative, right? This turns out to be like this more than it does like this. It is not a simple case. It is not a small perturbation to Dijkstra's algorithm. It's an entirely different problem for this reason. Dijkstra is greedy. Everything is nice. It's beautiful. It's elegant. You throw negative edge weights in there, suddenly you're in a very topsy-turvy, really horrible situation. Bellman-Ford is the algorithm named, I don't know if his name was Bellman-Ford or if it was Bellman and Ford, but whatever, he solved the problem of how to do this with negative edge weights. It's much uglier than Dijkstra's. There's none of the elegance, but it solves the problem, right? Before we get into what this problem is, how is it solved, and so on, let's just talk about, like, why doesn't Dijkstra's work, right? Everyone, including me, when I first took this course, was like, I didn't really get, like, why Dijkstra's doesn't work on negative edge weights, because it's in the same way, like, Kruskal's works on negative edge weights. Why? Say more. How does Kruskal's work, first of all? Property. Sure, but what was the code of Kruskal's? Yeah.
It's the property that the minimum edge is always going to be a part of the spanning tree. It's always preserved.
The minimum edge of the graph may not be part of the spanning tree necessarily.
Edge.
Of every cut.
Yes.
It's part of some MST. That's also true. I guess what I'm looking for is, like, first Kruskal sorts the edges and then chooses them according to the minimal property. It doesn't really matter if they're negative when you sort, because you can still make that comparison. That doesn't really seem to affect anything. But in specific for minimum spanning trees, that's fine. But shortest paths require a different perspective on localness that kind of is totally alien to the minimum spanning tree problem. So here's the first problem. Let's suppose you wanted to try Dijkstra's, but you have a graph with negative edge weights. What's the first thing you would think of to do to apply Dijkstra's? Something everyone comes up with, I think. Yeah.
Could you just add the same amount to every edge weight so that it all becomes positive?
Yeah. Now that's the first thing everyone tries. It's like, why can't I just pad every edge by a certain amount? Certainly all the comparisons and all the math should still work out. Well, the problem is it doesn't. Here's the counterexample. Suppose we're going like this. What's the current shortest path from A to B? The top. Now let's say you add one to every, let's say you add 2 to every one so they're not 0. I said 2, sorry. Now what's the current shortest path? Yeah, it's perturbing the edge weights in such a way. The connected properties of the graph, it's not simply the weights of the edges, but the number of edges as well, in fact. So such a thing is not going to work. This is a simple counterexample. There's another problem when you have negative edge weights, which Dijkstra's never has to consider, but unfortunately is a big problem. Maybe, yeah. What's the shortest path from A to B? Yeah?
There isn't a shortest path.
Yeah, basically. Now, the algorithm, Bellman-Ford, is still going to have to work in the... You don't know when a negative cycle exists beforehand unless you did pre-processing. So there's convention. We bring in convention. Like, what do you do here? You would say the shortest path from A to B is either it doesn't exist or it's negative infinity. It's not the case that you could, conventionally, what do you do? It depends. Sometimes you can say, part of Bellman-Ford as well is it allows you to detect if there's a negative cycle. So that comes with the algorithm for free. And sometimes what you can do is, again, it's convention. You can just throw out the answers. It's difficult to say the shortest path to accept the negative cycle. That's a very kind of a difficult problem and is not very important. So what we just say is just ignore it. Just like if the graph has a negative cycle, just throw out the graph. Just say I'm not going to solve that. Yeah.
In what context would a negative cycle actually show up and have a meaning?
That's why Dijkstra's is much more popular than something like Bellman-Ford. Negative edges are very unnatural, right? Negative numbers, by the way, aren't even real. Debt isn't real. It's made by capitalists. You owe the money in the opposite direction. That's all that really matters, right? Why would you ever do that when you can just do that? Right? For most practical problems, it's an issue of orientation rather than actual negative weights. For example, what would you want as to solve with graph problems? Let's say literal shortest paths in the sense of distance. You cannot have a negative distance between 2 points, right? Let's say you're talking about latency. It's a number of milliseconds between a signal between two servers. Time is also positive valued. Time, distance are all positive valued. You can't have negative value things. Now, there are sometimes you do want negative weights, and I think the classic problems are the word problems are always with debt and so on, like exchange rates of negative, something like this, or tolls, or something very contrived. But it never really makes good enough sense. And a lot of times you can reformulate the problem to be positive edge weights. That doesn't mean you should never solve the negative edge weighted problem. Sometimes you can't. A lot of times you can't. So it's not a very important problem, but we know that Bellman-Ford does solve it. Right? More questions, just before we get into the algorithm. Right, so let's recall why Dijkstra's worked and what doesn't work anymore with Dijkstra's, right? Recall we had a priority queue and things were entered and exited from the priority queue. We had V1, let's say V2, and V3, let's say this was 12, 23, and 40, right? And those are the current priorities of something in the queue. As you read through edges, you update shortest paths, and you pop things out of the queue and you push them back into the queue, right? You never have to push them back into the queue. Dijkstra's is greedy in the sense that if this is the current view of our priority queue, we know that the shortest path from some start to V1 is currently not going to get shorter than 12. Because we know it's not going to get shorter than 12, we know 12 is the shortest. And the reason we know it's the shortest is because the current, if there was a path through some other vertex, those are already longer. So if those update is all, they're not going to get shorter than 12. So we know that any of the paths that go through V2, V3, and so on are going to be longer than 23 or 40 and so on, right? So we know that this is the shortest path for V1. So it's allowed to make its exit from the queue, right? So Dijkstra's has this property only because edge weights are positive. There are no negative edge weights. Now, when you throw problems in with negative edge weights, you get a non-greedy property. For example, it may require something expensive to do something cheap. Let's see. Something like that, right? So you may have to get, let's call this S and let's call this A. Things may have to get worse before they could get better. Dijkstra's does not recognize this. It doesn't need to. It doesn't agree with this. Things always get better for Dijkstra's. Short paths only get shorter with Dijkstra's. They start at infinity and they only update if they're smaller. Recall we take the min, right? If it's less than it, then we take the smaller of the two and so on. And we repeatedly do this. So every time, shortest paths always get smaller. But as we see here, the shortest path things may have to get worse before they can get better, right? And that explicitly makes it a non-greedy kind of problem than specifically a greedy one. You have to, it doesn't know to get worse before it gets better, right? So really, one way to think about Bellman-Ford is you don't have a priority queue where things that exit the priority queue are never pushed back in. Because it could be the case that you found, it's as if you took a longer route to find a power-up that sped you up to get somewhere shorter, right? That's the problem that needs to be considered. So it's not the case that once something exits the priority queue, that it can never be entered. So really all Bellman-Ford is that if you have a priority queue, you have negative edge weights, and forget the negative cycle thing for a second, it has the property that things must be inserted back into the queue, right? So this V12, although you may think it's the shortest path now, there may be an edge of negative 100 somewhere that finds itself to V1, so then that goes back into the queue for some way, right? But then why need a queue? We don't need a queue. Forget the queue. We redo, Bellman-Ford is again Dijkstra's without the nice queue properties. So we don't use the queue, we use the array. Bellman-Ford is just Dijkstra's with an array that's repeatedly updated over and over so that until we know that we don't need to update it anymore. In that sense, it's just a less beautiful and uglier version of Dijkstra's. But if you agree Dijkstra's work, it's easy to see why Bellman-Ford works, right? What do we mean by update? I keep using this word update. So if we have something of the form, let's say we're at some intermediary step. We have, let's call this S, and we have a current path to some node U. This is stored as a value of dist U currently, and then we have some node V here. And this is going to be dist V, right? And then we have an edge here of LUV. Do you recall in Dijkstra's what we did if we saw such a scenario when we looped over U this way?
Added this 2 plus the edge and saw if it was smaller than what was previously set for V.
Yeah, we said if dist of U plus LUV was less than or equal to the current dist V, then dist V takes on that. And then we set the shortest path to V to actually go through U. So what we really did was we took the min, we said that dist V takes the min of the current dist V, or the dist U plus L of UV. And every graph algorithm of shortest paths actually kind of relies on this kind of primitive in some sense. And this is called the update. So we're going to perform updates on the graph according to this, but we're not going to have the nice Dijkstra properties. We're just going to make sure, this was in the core of Dijkstra's, if you recall. It wasn't a min, there was actually an if, which one was less, but same thing. This is the core. So we're just going to throw this at the graph over and over until it gets what we want. It's going to be slower. Let's just throw this in a for loop, okay, over the whole graph. If we loop over, let's say we do this over the whole graph once, right? What have we really computed if we've done this once? Yes?
The neighbors.
Yeah, so like, we've done it only once. We really only know shortest paths of how many edges? What is neighbors is what? What is an edge, really, if not a path of length 1, right? So you throw it in a loop once. If you do this over the graph one time, you have computed, in some sense, shortest paths with one edge. So if you do it over the graph twice, you've computed shortest paths of, at most, 2 edges, because things update the update. And the previous update was the shortest paths of length 1, and so on, right? So if you do this over the graph I times, you're only considering shortest paths of length I, right? So we need to do this over the graph over and over and over until we know that we don't need to do it anymore. So how many times do we need to throw this over the graph? E times. There's a shorter bound, I'll tell you. That is correct, though. Can you give me something smaller? In a graph V plus E, what is the longest path? That's kind of what we're looking for. What is the length of the longest path? Yes.
V?
But a cycle contains V.
Oh yeah, I guess, but if you consider either it has a negative cycle, so it kind of does that. But if the cycle is not negative, then taking the cycle doesn't actually make the path any shorter.
We'll have to append the negative cycle on it in a second, but for now just consider, suppose positive edge-weighted, right? What is the longest path that can exist in a graph? Path. If it's a cycle, it goes back to it and there's a shorter path, in fact.
V minus 1.
V minus 1. Why? V vertices, if you go through all the vertices, those are 4 vertices, 3 edges, right? So 4 vertices would use 3 edges. You have V vertices, the longest path can exist is V minus 1. So all Bellman-Ford, I mean, that's it. That's like why it's so ugly. Bellman-Ford, you just do that V minus 1 times over the whole graph. Yeah, not really, not very pretty. Let's just let me give you the code. Def Bellman-Ford. It takes as input G, the weights, and a start node S, and we'll solve the negative cycle problem in a second. But first, let's talk about how to do this. So, for all V in V, dist of V takes on infinity, and we say dist of S takes on 0. For I equals 1 to V minus 1. And then for each edge, we take the min of, we say, what is it, dist V takes on the min of dist V or dist U plus LUV. Okay, that's it. That's all Bellman-Ford is. Much uglier than Dijkstra's, less aesthetic, everything, etc., etc. What's the runtime? Sorry? Yeah, not too good. If the graph is dense, what is this?
V cubed.
Yeah. Not good. Can you do better than this? It's actually an active area of research. Can you solve shortest paths in graphs with negative edge weights faster? Yeah. The answer is there was even a paper as recent, I think, as like 2023 that solved this problem. It was in the news. They still managed to figure this out. And they use very complicated techniques. But know that they're still improving this. Bellman-Ford is simply the relaxation of Dijkstra's if it has to deal with negative edge weights. Why? You got to put stuff back in the queue. So instead of the queue, we just deal with the array. You repeatedly throw the updates at it as many times as you need. Does anyone recall the runtime of Dijkstra's? V plus E log V, right? It's data structure dependent. It depends on the array and so on. Either way, far worse, far, far worse in runtime, right? If the graph is dense, again, what is Dijkstra's if the graph is dense? Yes. Just replace E with log V, right? And then big O stuff around. Okay, so like that's significantly worse of a runtime, but we're happy that it works. So it works. Okay, fine. Doesn't help us with the negative cycle problem. And again, what you do with the negative cycles is your convention. Do you say, I throw them out, or do I assign the dist values to be negative infinity or so on? It doesn't really matter. Let's just say we throw them out. If the graph contains a negative cycle, let's just toss it. How can we use this to determine if there's a negative cycle? We have some information so far. How can we use this information to determine the position of a negative cycle? What do you know about shortest paths in the case that there is a negative cycle, right? Yes?
All the shortest paths are going to end up in that cycle.
Not necessarily. Something like that. The shortest path, the negative cycle, if the graph contains a negative cycle, it only is going to change shortest paths that happen to go through that negative cycle, right? But suppose our graph does have a negative cycle and we're doing an update like this. how can we use the updates, information that's updated, all that, to determine if there is a negative cycle? Yeah.
To update something, run it again after doing it v-1 time, and if you have to update something, you know there's a negative cycle.
Yeah, exactly. So here's what you do. Run the for loop for an additional time. Run loop one more time. If anything changes, then there exists a negative cycle. You run this update, this loop at the top one more time through all the edges. If anything changes, you know that there's now a shorter path that is of length v, and that shorter path uses v edges when the previous shortest path used v minus 1. So if that shorter path uses v edges, you know that it must, if there's v vertices and v edges, it must contain a cycle. So in fact, if it's a shorter path that has a cycle, it must in fact, it can only be the case that it's a negative cycle. So we can detect the negative cycle by running update one more time. And if anything changes, we know there's a negative cycle, right? And convince yourself, were we to run this update 10 more times, values would decrease all the way and repeatedly to negative infinity, right? If we repeatedly to do that update, you would see values decrease only when there's a negative cycle, because that shortest path would go through the negative cycle over and over, right? Questions on Dijkstra's before we just run through a quick example? I'm sorry, on Bellman-Ford? Again, not very pretty, not very elegant, has none of the beauty or whatever that Dijkstra's have, but that's okay. It works. Sometimes that's all you can ask for. So let's run through Dijkstra's really quick on a graph, a small one. So, sorry, Bellman-Ford. Okay, and suppose that we have a sequence of rounds here. So let's initialize, at round 0, the array is going to be initialized with what values? Yeah. Round 0 is we're going to begin with 0, infinity, infinity, infinity. Okay. Now run an update through all the edges. What is the current shortest path? For each edge, we take the min of the current shortest path, the current dist value there, and if that edge changes anything. For example, this edge of weight 10, we have 4 edges, so we're going to do our internal loop of length 4. S to A, we're going to take the min of dist A with dist 0 plus 10. So what's 0 plus 10 is 10? Is that less than infinity? Yeah. So we're going to update dist A to be 10. Dist S is never going to change, right? What about dist of B? We have an edge here, S to B, which is 11. So 0 plus 11 is less than infinity. So we're going to update that. And what about dist C? Dist C, now here's the kind of, Bellman-Ford is interesting because there's lots of little implementation details you can do. First off, when we read dist B, do we read 11 or do we read infinity? Yeah, it depends. Like when you actually do it in the reason we write it like this is to read the previous dist value. So we're going to read infinity plus this infinity plus 12, which would not update it, right? So this is in fact going to be infinity. Now practically, when you actually do update the array live, it's going to be 11 plus 12. But the way we'll consider that is the next round. So we take the dist values of the previous round. It's not anything important, it's simply a convention. And definitely if you implemented this to look at the current round, it would simply speed things up. But only by constant factors, which is what Big O would ignore, right? And this was round 1. Suppose we're in round 2. The shortest value to S is still going to be 0. But dist A is going to have its Is that going to update with anything? No, because this edge is going to be infinity minus 20, which is not going to change anything. S to A is also going to not change it, so that's going to be 10. What about dist B? Is dist B going to change? We also no. What about dist C, though?
Because you're looking at the previous round, it's gonna update.
Yeah, it's going to be, dist B is currently 11. So 11 plus 12 is 23, which is less than infinity. So this is going to update to 23. Right. That's it. Okay. Dist S, none of those edges are ever going to go into S ever again. What about dist A? Why? Dist of A, just to outline what's going on, dist of A is currently 10, right? But it's going to take the min of dist of A, which is 10, and dist of what? C? C, which is currently 11? No, 23. And it's going to say plus the length of C to A, which is going to be negative 20, right? So what is that? Yes?
This update only runs when we loop over the edge C to A, right?
Correct, correct. The update, the for loop is the round over V, and then the internal for loop of E is over the each edges. So we're going to look at edge, 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 right? And maybe I'm not doing the best job of looking at them in order, but that's definitely an edge that's going to update something. So we're going to say dist A is going to be 3, because you take the min of 10, and 23 minus 20 is going to be 3. Okay? Is dist B going to update? S to A is going to be 11. That's not going to change anything. And nothing else goes into B, so that's going to be fine. What about dist C? Is dist C going to update? Nothing else goes into it except B to C, which is 12. And B was already still 11, so that's 23 still. Okay. Done. You can generalize and imagine this worked on a larger graph. This is all Bellman-Ford is. It runs on negative edge-weighted graphs. One more engineering speed up that you may notice. There's another way to speed up Bellman-Ford by a constant factor. What is it? Let's see if anyone noticed it. Yes?
You don't ever need to update the source.
Oh, they're,
Be a negative cycle.
yeah, okay, but, okay, sure. Let's suppose it's always 0. There's another speed up. Suppose you have a graph. We said the longest path in a graph was v minus 1. But this is a worst case thing. What if the graph is really triangular in the sense that the shortest path is like 3, but you have like 1 million nodes? Yeah.
Once it stops changing, you don't
Yeah, in the big for loop, you keep updating, you keep updating, you keep updating. You go to v minus 1 simply because that's the longest possible path. But if at some round, the middle round, let's say, the next round doesn't update any values, like let's say we ran for one more round, we did 0, 3, 11, and 23. If an update doesn't change anything, the next one won't change anything, and so on, right? So if at some middle round, let's say the v over 2th round, the update function changes nothing, just give up. You've found the shortest paths already. The round considers paths of lengths I, for I is that variable in the loop, right? So if the longest path is not v minus 1, if it's like 3, then just stop after 3, right? Big O, how much does this save? It's at most a constant still, right? V over 2 is big O of v. So if the shortest path is half the number of vertices, the longest path, excuse me, is half the number of vertices, that doesn't matter, it's still a constant. But it is definitely an engineering speed up that is very important. Question?
This also stops negative cycles, right?
Yeah. The negative cycle case is convention on how you handle it. Right. Questions on Bellman-Ford?